Okay, let's roll them. Okay, so the projects, I haven't, we haven't started going through them yet. So I guess at least I haven't seen the results yet. I don't have any data for you on that yet. We'll hopefully try to do it next week or so. What's happening? Okay, so as you know, you have this feedback homework set, which is due Wednesday. There'll be one stability, which will be due the following Wednesday, and then we'll do the last project, and that'll be due in 3 weeks into the semester. All right, and we'll do after the next project. I'll do stability. I'll do some compensation, the final design work, and those lectures will probably finish in about 2 weeks, 2.5 weeks, and then we'll do some. I'll probably go do some RF design, radio frequency design. You know, sort of inductors. That's basically add inductors into the whole world, and so we'll do a little bit of that. Unfortunately, we won't have any problem sets on that. I was thinking about. Okay, I'll ask you if you want to do this. We could do a sort of a. We could hand out a problem set for you, okay, and it could be sort of optional, okay. And I thought, well, we could make it optional with a little like extra credit. Now, what does that mean? Okay, I mean, so if so, I was trying to figure out some strategy where you had some reason to do the homework, but not so much. I don't want to have a homework and a project at the same time, unless you got the extra time to do it. I guess I'm open for ideas. If you got some ideas on some sort of, you know, if you do the work on it, and if we're going to grade it for you, you got to get some kind of little bit of something. You know, I could just say a pat on the back, and I'll look and I'll see when I do the final grading, I'll look to see if you did that. But that's, you know, that might scare you more than if I had some more, you know, defined way of dealing with it. Yeah.
So is the art stuff will be in the final? Or just in homework?
I'd like, well, there won't be any homework. That was my problem, right? I'd like to have it on the final because I think it's important for you guys to at least think that stuff through a little bit. So that's what I want to do. I think I'll have an optional homework, okay? And so we'll have solutions, so you can look at how the problems are worked and you'll see the solutions. Whether you have to turn it in or not or something, if someone can help me figure out some extra credit of some sort. If we can figure out something for that, we'll give you a little extra credit for doing that little homework set. And we'll probably have at least one little problem on RF design, just so you listen to me right in the final. Okay? Yes. Use a mic. Yeah.
Well, I think a lot of professors, they just like put out a homework and make it not due, and basically just like put out the solutions, and basically so you have time to work on it like before the final. And so like if you do it before the final, I mean you've pretty much learned the material, and then you can actually test on it.
And don't really give any extra credit for it.
No, just like
because it's on the final, it's the
test.
test.
On the final, yeah, you better know it. Otherwise, it's kind of bad.
That's a reasonable thing. Yeah, that sounds.
But
That's kind of what I was thinking about.
Extra credit would be a better idea.
What? Extra credit would be a better idea. We'll take a vote next. We'll take a vote before this. I mean, when I figure out what we're going to do, okay? And you think about what you want to do there. I can see both sides of it. I mean, once I say it's extra credit, then it becomes almost mandatory then in some sense, which is kind of the problem, right? And that's what I didn't want to do, right? So that was kind of. I do. Okay. So that's coming up. That's a few weeks off anyway. So we can keep that discussion going. Anything else? Any other questions or anything? Okay, what I'm going to do, a little bit more on feedback, since I know you really got that all understood pretty well right now, so we can move right on. Maybe not. Okay, so I'll do some more examples. I think the thing about feedback, first, the single transistor circuits that we did are probably some of the most difficult to identify what kind of feedback it is and so on. So maybe don't get freaked by that, because generally you can define, you can look at it, you can sort of see a few common source stages in a row. Think that looks like a basic amplifier. You see some stuff coming back around, and that looks like the feedback network. So usually it's a lot simpler. But that being said, let me give you another one that's kind of difficult. Okay, so because I think if you can understand these difficult ones, you can do the easy ones, right? Okay, so let's do this one. Okay, here you go. Our favorite circuit. Okay, anybody recognize this? Does this look like something you've seen before? What is it? It's a Wilson. It's a Wilson current source where IN is equal to I ref, right? And we sort of know the answer. What's the relationship between I out and I in? It's 1, right? I mean, I out equals I in. So that's a little clue for you that probably the feedback factor, this is a feedback network, as we talked about, and the feedback factor is probably 1, right? Okay, so now where is the feedback? What kind of feedback is it? Let's ask that question first. Who can take on that one? What kind of feedback? Taker?
Series shunt.
Series shunt. Okay, that one's on the table. Let's see why. Okay, series shunt. Okay, why? Okay. Use your mic. Okay.
The source of the transistor is sensing the current.
Okay, so I out goes into here, and I out comes out here.
So it is shunt.
So it's shunt. It's something series, right? So what's happening? So what kind of sensing are we doing?
Current.
Current sensing.
Yes.
Okay, so this is the type of feedback. And this is the type of sensing. Okay, so now are we sensing in shunt or in series? Okay, maybe we'll change this. Okay. So it's series sensing, right? Okay, that's good. Okay, so we have I out here. We have, and this, if I out's flowing here, this is mirrored over to here. So we have I out flowing over here as well. So what type of feedback do we have? Shunt. Now why is that? Here's the input coming into this node. Here's the feedback. So this is equal to the I feedback current coming out of here. So what is flowing into here? This is the I error, right? These are in parallel with each other. So this is shunt feedback. So you almost had it. Just compliment, not, right? Okay, good. That's good. I mean, that's glad you tried. So, okay, so we have, so you can see that? It's series sensing, because we're sensing a current. I mean, here's the output up here. We're not connected to the output. Even if we defined a V out up here, we're not connected to that, right? We're connected into the source down here, but that's, and typically when you have the feedback start from the source and the output's in the drain, you're doing series sensing. That's pretty much just the rule. That's, people asking me, what is the rules I can use? Well, that's a pretty good one, right? If the output's up here and you're looking down here, you can't be connected to, you can't test what the voltage is. You're not connected. Excuse me. You're not connected to it in any way. And since we know the current in here is the same as the current out there, you're sensing the current then. Sensing it back here, when you're sort of in parallel like this, there's no place I'm developing a voltage. I mean, in order for this to be series feedback, I have to have V air equals V in minus V feedback. I could turn this, if I have an R out here, I could turn this into some sort of voltage in network here. But is there some way that I'm developing a voltage that I'm differencing with some voltage up here? And there's not, right? And so this has got to be a shunt feedback. I mean, I guess you could figure out the feedback by two things. One is you can try to see what it is, or you can try to see what it isn't, okay? And if there's no way that you can sort of see that there's a voltage being differenced anywhere, well, then it's got to be currents. Then you can sort of work on that and figure out where the current sensing's, where the current summoning's going on. Okay, so this is shunt series feedback. So now let's figure out, so what is our basic amplifier? The basic amplifier really is simply this guy right there. That's the basic amplifier. So if we look at it by itself, so here's I out, and here's I air coming in, and this is connected to something down here. And to start with, this is the basic amplifier. It's an open circuit. You think, wow, got a current going into a gate, which is sort of infinite gain. I have a open circuit on the source, which is kind of where can the current go there. So things are really fouled up. Things don't usually work out in these circuits until you put the loading effect of the feedback in. Okay, so now let's put the loading effect of the feedback in. The feedback network is simply this, right? So here's I don't know why I'm using capital letters here. This should be all lowercase, right? I in of the feedback network goes into here. That's going into this gate. And then it comes out on the other side. And this is I out of the feedback network. All right? So here's I out of the feedback network on the other side here. So this is our feedback network. So here's our basic amplifier, and here's our feedback network. Okay? What's the feedback factor? I out feedback over I in feedback. And we can work this out with small signal, but we know the answer is simply equal to 1, right? I mean, this current here is equal to that current there. So this is equal to F. So F is equal to 1. Then we have to figure out the loading effect. So what is the resistance looking into this lead, the input to the feedback network? Well, what do? Looking into here, what do we do with the output over here? Well, we look into here to figure out the input resistance. What do we do with this output? Do we short it or open it? We short it, right? Because it's a current output, so we short this output. It actually has no effect on the input resistance anyway, so it doesn't really matter. But looking into here, sometimes it does matter, right? But we short this side, we look and see what resistance we see here. So looking into here, what do we see? We see, let's label these transistors. Let's call this 1, 2, and 3, okay? So this is 1. So looking into here, we see simply 1 over GM1. Okay? Looking into here. So that is the input resistance of the feedback network, and where does it connect into our basic amplifier? Well, it connects in right here, because the output, the source of our basic amplifier is connected to our feedback network, and now we're seeing an effective resistance of 1 over GM, so I can put the resistance here, and it's 1 over GM1. Okay? Now, what about the output resistance of the feedback network? So looking into the output here, that's the output resistance of the feedback network. What do I do with the input to the feedback network when I'm looking at the output of the feedback network? Shunt, short, or open? Open. Short. That's the two choices. You got it covered. You got it right. Absolutely correct. Okay. Now, which one? Open. It's open, right? We're looking at the input here. The independent, another way to think about it is there's a independent source here is current. Set it to 0, that's an open. It's series, that means it's an open. What else can I say? I guess that's it. Okay, so the ideal, so it's open. It still doesn't actually affect anything to do with the output resistance here, but might in other circuits. So looking into here, what do I see? I see, this is transistor 3, I see R03. So R03 is the loading effect of the feedback network on the basic amplifier. Okay? And if I had anything more connected to this node, it'd always all be in parallel with this R03, right? If there was resistance up this way or anything else, it all included as part of this resistance right here. Okay? Now, what is, okay, let's calculate now A sub I. A sub I is the current gain. It's equal to I out over I air, which is the current coming into this network. Oh, wow. So what is it? Well, let's first calculate VG2. VG2, the voltage on the gate of 2, is simply going to be I air times R03. I out is going to be G sub M2 times VG2, but degenerated, right, by 1 over GM1. So I can degenerate that. So it's 1 plus GM2 times 1 over GM1. Right? It's like an RS down here, right? Yes?
Isn't it like VG2 equals to I out divided by times R3?
VG2 is equal to I out. Well, I'm just doing the basic amplifier now, right? So I called this current going into the basic amplifier I air, right? I should redraw this. This is looking. Let me redraw this because this is actually not quite. I have I air defined here. I have I out here. Let me redraw this a second here. So here's my I in. It comes in, and let me do it like this. This is I out of the feedback network, and this goes into R03, which goes into my amplifier, basic amplifier. Here's I out. This is transistor 2, and this is 1 over GM1. So what I've done here is I've, in this I out feedback, if I included it, is equal to F times I out, right, which is equal to I out. So this is kind of, so there's a, this is kind of the whole, this is with the feedback network, and this, and if I look at this, here's the basic amplifier right here with its loading effects, and here's I air coming into here. So this, you could say this is the, so I'm trying to do now is get the basic amplifier, and I could call this equal to I in of the basic amplifier, okay, right? It's the current going into here. So I call it I air, but, and, okay. So what I want to do now is find the two-port model of all, including all of this, right? And the two-port model of this going into here, I see an R03 to ground. On the output, I see a current source, okay, and let's call this A sub I times I error, and then there's an output resistance associated with that current source, right, and we'll call this R out, and here is I out, all right. So now, what is AI? Well, that's AI is what I just calculated right here. AI, if I substitute VG2 equal to I error times R03, and for VG2, I get I out equals AI times I error, and AI, this is the current gain, right, because it's a ratio of I error to I out over I error, is equal to GM2 times R03 over 1 plus GM2 over GM1. So this is AI. T, this is with loading now, right? So this is the prime. T prime with loading is AI prime times F. Well, that's just simply the same as AI because F is equal to 1, right? AI prime. All right? So now I got T prime. Now, what I need to do what I need to calculate is what is R out, okay? So R out, looking in to here, okay? So we'll set the independent, we'll set this current to 0. So looking into here, what I'll see is the current source inside here will be gone, right? And I'll see, so let me just redraw that. Let me redraw that for you. So I have a GM times VG2, right? And then I have a R03, and here's a VG2, and here's an I error, and here's an, I'm trying to calculate, looking into here, R out, and I have an R0 here, and then I have a 1 over GM1 down here, okay? So by that, this is the same as this. Well, I error, when I'm calculating the output resistance, I set the independent source to 0, so I set this to 0, VG2 is 0, so that means this goes to 0. So R out is simply going to be what? R0 of transistor 2, R out, equals R0 transistor 2 plus 1 over GM1. Okay? So far so good? So this is R out of our basic amplifier with loading. So this is little R out, I guess. I'm sorry. This is little R out. Okay, little R out. It's just R out right there. Okay? So this is equal to R02 plus 1 over GM1. Okay, now what is the output resistance looking into here? Do I increase or decrease the output resistance looking into here by 1 plus T? Increase or decrease? How's that? Increase. Why is that? Series bigger. We know the answer. This is a big high output resistance here, right? So, R out of our whole, this is a closed loop R out. This is looking into here right now, is going to be equal to little R out of the basic amplifier times 1 plus T prime. Well, little R out we decided was equal to R02 plus 1 over GM1 times 1 plus, and T prime is equal to GM2 R03 over 1 plus GM2 over GM1. What's this? 1 plus GM2, that's approximately equal to 1, let's say, this ratio here. So this is equal to R02 plus 1 over GM1 times, and this is probably small compared to R02, right? So we get rid of that. 1 plus, and this is GM2 R03 over 2. So R out is equal to R02 times 1 plus GM2 R03 over 2. So it's big increase of R02 by 1 plus GM2 R03, and that's what we calculated a while ago, right? Earlier on in the year. Even with the factor 2 even there, right? So this is a really good example, I think. I mean, this shows you, this is the feedback, this is the Wilson source. I told you it was feedback early on, right? And the reason this is a high output resistance, because it's a shunt series feedback network. It's the series sensing at the output that makes that output resistance really high. Okay? So that's pretty classic kind of problems we'll give on the final, if you're interested. I mean, what kind of feedback is it? Calculate the basic amplifier gain, calculate the output resistance, calculate the input resistance. What's the input resistance? Maybe we should do that one. This one's not. This is not something relevant to. So here's I in. So what is the input resistance looking into here? So that's kind of interesting. So what is R in? R in of this circuit is going to be what? It will be equal to. So R in is going to be equal to little r in divided by 1 plus t prime, right? Because it's a shunt feedback, so it's going to be divided by 1 plus t prime. And what's little r in for this circuit? Well, we can look over here. Little r in this circuit is R03, right? So this is little r in. It's equal to R03. So this is equal to R03 divided by 1 plus, whatever it is here, GM2 R03 over 2. Right, so that's what Rn is. That's what looking in here from the reference current source is. Okay. So what does that equal to? Let's say this is greater than 1, so we end up with about 2R03 over GM2 R03. R03s cancel, so we end up 2 over GM2. So looking down into here, we see 2 over GM2. And that's not too obvious, right? If you look at this circuit, you're looking into R0 here, you're looking into gate there, but the resistance looking into here is really 2, this is really equal to 2 over GM, because it's the feedback that's causing that to happen, right? Current in, you'd like it to be small resistance. It is small resistance. It's 2 over GM. Current out, you'd like it to be high resistance. It is a high resistance. It's R0 times GM R0. So you can sort of see why we have to go through. I mean, feedback's pretty tricky stuff, right? I mean, you look at this, you kind of, once you start getting this feedback going on here and you get lots of loop gain, you've got to sit down there and be more rigorous about how you analyze these circuits. You've got to identify the feedback. You've got to just go through all these steps we talked about. Right? Okay, any questions about that? Shall I do another little feedback problem? Let me just create some here. I think so. Let's do one like this. Let's take. Oh, I know. Here's one. Okay. Okay, let's take this as V out, and I want to connect this back into this circuit through a feedback. I want a gain of precisely 10. Okay? Voltage gain of 10. So this is, let me, okay, so I want V out over V in equal to 10. No, plus or minus. I can't remember. Polarity is going to be plus 10, I guess. Okay. How would I connect the feedback to make that happen? So here I got a basic amplifier. I have a differential input, and I have another gain stage, something you guys have seen before, I think, right? And okay, how would I connect this back so that I can get a voltage gain of 10? Okay, plus or minus. I'll have to figure out what polarity we can get in a second. Any takers? I want voltage in, voltage output. So I probably want, what kind of feedback do I want? Voltage input means I want series type feedback. And what kind of sensing do I want? Shunt. So I want a series shunt network. So I want to connect right to this output, and I want to somehow feed it back so that it's in series with the input. Now we know that the voltage, the gain from here to here is equal to what? Let's call this V in, let's call this V1, let's call this V2. We know that the voltage gain to there is, call this V01. V01 is equal to V1 minus V2 times GM. Okay? GM of, this is 1, 2, right? GM of 1, let's say. And these are the same transistors and so on. We've got a differencing going on here. So this is kind of interesting. So we've got a nice, easy way to difference the voltage. If I put the input on one side and put the feedback on the other side, if I do have V in on one side and the feedback on the other side, sure enough, I've got series feedback. Now the question is, where do I connect this? Now, I got to go through some sort of little resistor network to do this, but which side will I connect to? Anybody tell me that? Do I connect to V2 or do I connect to V1? V2? Okay, why? Get your mic. Give it a shot. Okay, he said, let's connect to V2. So let's say I take a resistor out of here and I connect to V2 and I do this. Some sort of resistor network connecting back to V2. Okay? Sensing the output, that's a shunt sensing, and I'm feeding it back to V2. So why did you choose V2?
Because like V2 is kind of the negative feedback node.
Okay, so let's go from here. So V2, let's say it goes up. What happens here?
Goes down.
Goes down, right? Cross an inverter, you always can change the polarity. So I go up here, I go down here, I go from here, I'm going down, so I'm going down on the gate of this device. Then I go up, then what am I doing here? Going positive here, and this little resistor divider doesn't change polarity, so what am I doing? I'm in the same direction. So what kind of feedback is this? Positive feedback, right? So what do I need to do? I need to connect this over to here. So instead of, so what I need to do is put V in here, break that, and do this. So take this output, go through a little resistor divider network, and connect over to here. And then I'll have negative feedback. Okay? Shall I redraw that? Let me redraw that. Let me just. This problem's getting so complicated. I'm getting messy too quickly. So let's that's a resistor. Okay. Oops. And where do I put the input? So I want to do V. So this is V feedback here. So I want to put the input over here. Okay. Let's call this R1. Let's call this R2. Okay, so what is the F factor for this circuit? So I drive, so here's V out. So F for this circuit is going to be equal to what? Okay, which mic? Okay.
R2 over R1 plus R2.
Okay, so how'd you get that?
Just a voltage divider.
Right, exactly. So V feedback, this equals V feedback over V out of the circuit, which is the V in of the feedback network, right? This is V in of the feedback network. So here's V out of the feedback network. So basically, I just got a little voltage divider here, and you just calculated it for me here, right? So that's exactly right. If we have lots of gain in this circuit, which we probably do because we've got a differential pair followed by a common source, if things are biased right, may not have lots of gain, right? But if we did, okay, then what would be the V out over V in? What would that be equal to? 1 over F times T over 1 plus T, but let's assume that's large, so it's just 1 over F. So this equals to 1 over this, which is R1 plus R2 over R2, which is equal to 1 plus R1 over R2. So if I want to gain a 10, what do I have to do? I have to make the ratio of R1 to R2 a factor of 9. So if I make this equal to 9K and I make this equal to 1K, then I have V out, the ratio of V out to V in is 9, 10. What is it plus 10 or minus 10? Who can tell me? The way to do it is just start here, go up. This means this node goes down. If that node goes down, this node goes up. Right? Even the feedback's there. You can still keep track of polarity that way. So V in to V out is positive, right? So that means it's a plus 10. Okay. While we're going for it here, let's go for the... So here's our basic amplifier. So let me redraw it again. And now let's include the loading effects on our basic amplifier. Okay? Excuse me. So here's our basic amplifier, here's our second stage, here's our current source, here's our output. Okay. Here's VN, and here's our... So what do we connect to here? To this point right there. So from here, we need to look back into our feedback network. What kind of feedback is this? We decided it was series shunt, right? Okay. So looking into here, what do we do with this side? Short it or open it? Short it, right? Why is that? Shunt equals short. It's an output of a voltage. An output of a voltage is low impedance. Okay, so this should be shorted on this side. So if we short this side, that means looking into here, what do I see? I see R1 in parallel with R2. So I have R1 in parallel with R2. Okay, so that's the loading of the basic amplifier on my basic amplifier, from my feedback network. Looking at the output, what's the loading going this other way? So looking into here, R1 and R2, what do I do with this side? Series, open. So I open it. what's that? It's R1 plus R2. So here I'll have R1 plus R2. So here's my basic amplifier now. Here's V out, here's V in. So what is A sub V prime? The voltage gain of this basic amplifier with loading is simply going to be what? It'll be the gain. Does this do anything here? Nothing, right? That just grounds this point, right? Doesn't matter, resistors here doesn't have any effect at all. So the gain from V in to here is going to be equal to GM times the R0 at this node right here, right? R0 over 2, like, parallel combination of these two guys. It's just the old gain of a differential pair, right, with current source load, times the gain from the second stage. Let's call this 1, 2, 3. R's GM1 equals GM2 and R01 equals R02, right? I get this. Times the gain of the second stage, which is going to be GM3, times the output resistance of this stage, what it's going to be? It's going to be R03 in parallel with R1 plus R2. So there's AV prime. And F, we decided, was equal to R2 over R1 plus R2, so T prime equals AV prime times F, this times that. What is R out? I'll do it up here. R out, looking into here, what's it going to be? So looking into here, I see R1 plus R2 in parallel with R03, right? R1 plus R2 in parallel with R03. And then do I divide or multiply times 1 plus T? It's a voltage output. It's shunt, series shunt. We divide by 1 plus T prime. Yes?
How come you can use the differential gain equation when you only have a single input now?
What's V input differential here? It's going to be, this is grounded on this side, right? V input differential equals what? This minus this, which is equal to Vn, right?
But they're not symmetrical.
There's a common mode signal that goes here, right?
Yeah.
So I didn't worry about the common mode part of this signal, right? So there'll be a small common mode component which will get to this output, right? Actually not, because I got a current source down here, right? This has infinite resistance, right? So, but you're right. I mean, generally we would have a finite common mode gain, but that's why we design these circuits to have large differential gain and small common mode gain, because we don't want the common mode gain, right? It adds a little response to this output that we're just not interested in. Okay. So that's kind of this is exactly why we ended up designing our circuits all the time with that large common mode rejection ratio, because what we are interested in is differential gain, right? And quite often you use circuits like this. And input resistance is what? Well, look here, it's infinite, but it's infinite times 1 plus T, so it's still infinite. So. Okay. What else could I do? Let me just try one more here, and we'll have a break. Can I do some other kind of feedback here? What could I do? Let's see. If I wanted to do some local feedback, could I connect this to here through a resistor network? That work? So I'm connecting the output. So that's like shunt feedback. I'm connecting into this. Oh no, what am I doing here? I'm over here. Right? Okay, so I do this. What kind of feedback is this? It's series again, shunt. And let's check the polarity of it. This goes up. This node goes down. If this node goes down, let's see if it's easier. If this node goes up, what does this node do? Goes up, right? So if this goes up, feeds back into here, up, up, what do we got here? Positive feedback, so this doesn't work. So you'd have to do some sort of, if you only have one stage, you have feedback locally like this. All you can do. One more? Let's do one more. Then we'll be done with feedback. Let's try this. Let's some bias voltage. Some bias 1, V bias 2. Okay, and let's do some feedback here. Let's see. Let's take this and let's see. Oh no, I want to do this. I want to do it like this. I'll make this V in and make this a bias voltage. This is V in. This is V bias 1 down here. Okay, so I got the input coming up here, and I got this down here. And let me take this. And let me put a resistor here. Okay. You see this now? So I come in here through a resistor. I go into the gate of this transistor. This is a source follower with a current source load. I come out of there. I go into what? Common source, and I feed back around. Okay. What kind of feedback is this? Where's the output? Good question. All right. That's an excellent question, actually. Okay. So needed to know that right away. Good. Okay. Now, what kind of feedback is this? Current voltage, which is shunt, right? We're feeding back in parallel, so that's in shunt. We're sensing the voltage in parallel. That's in shunt. So it's shunt. Is it positive feedback? Let's check that. So we go up here. This goes up. This goes down. And this goes down, so it's negative feedback. Since it's shunt, I got to convert this to a current source, right? I got to convert this to an I in, which is equal to V in over R in parallel with an R in, which I will then include as part of my basic amplifier. Right? Okay, are we all experts at feedback now? I'm certain you are. I have confidence. Right? So we'll have a break for 3 minutes to absorb feedback and wave it goodbye. Right? So you can have all the notes. I got some water.
So there's like telling like there's different types of feedback, right? But like, how do you tell if it's feedback?
You see something happen in the output, and it's kind of getting coupled back into the input somehow or other, right? If you sort of see it feed forward, and you see nothing coupling back, then you know you're okay, right? As soon as you see something from the output kind of coming back and coming back around.
Well, so first follower, like, how would you tell it was feedback? Because like,
That's tricky. I mean, it's it's a little hard to see that because I guess the reason you do it is because here's V in, right, and here's V out, and the amplification is happening from across here, right? That VGS is where the amplification is. So you look and see what that V error is, and you see, well, it's V in minus V out, and say, looks like the amplification has something to do with V out. So
basically, like, I don't know, like as a general, like, this is kind of a weird generalization, but like if you have something like an output, basically, like whenever your output's like attached to your source,
in any way, it's all, yeah, right. If you see a loop, right, there's feed forward, right? If you just go from this stage to this stage to this stage with all the circuits like we did so far, right? You just never is anything coming back, right? Right. And when you see something kind of coupling back into that source, you probably got something going on. Okay. All right. Okay. Let's roll them. This is getting towards the last of the, well, I guess it'll be three, so what's all the topics left? Stability. This is what we're going to talk a little bit now about what happens with feedback and frequency response together, okay? And so this is frequency response, okay, which is what we worked on a few weeks ago, plus feedback, okay? So what are the two things there? It's more than just stability. It's, bandwidths change. The frequency response of the circuit will change because of this feedback network. So we're going to analyze that, okay? Then what we're going to do after we do that, we will figure out how we have to change the circuit in order to make it stable. Because we're going to see there's some problems if we don't do some extra circuit changes. We call that compensation. Compensation is just what you do to the circuit in order to make it so that it works, okay, so it doesn't oscillate, okay? Then we'll do some odds and ends we have to deal with. Is the fact that with feedback, the transient response starts changing because some large signal things begin to happen. So we'll analyze that a little bit, slew rate. And then we'll do some of this little RF stuff. So that's kind of the rest of the year, okay? Okay, so here is, let's go back to our basic feedback network, and now let's add in frequency response, okay? Before we said A of omega was frequency independent. Now what we're going to do is allow A of omega to have a frequency dependent. So this was your second project, right? Was calculating the frequency dependence of this basic amplifier. Now what we're going to do, to start with, we'll put frequency independent feedback around it. We don't always have to do that, but let's start off that way. It turns out what we'll find is T, that's our loop gain, right, is equal to A of omega times F. And what's really important now, the loop gain will become frequency dependent. That's what's important. What we'll find is the important thing for us to look at in terms of stability is the loop gain. It's not the independent feedback or basic amplifier by themselves. It's the loop gain. So as soon as we put frequency dependence in one of these two blocks, we've sort of covered the general case. Okay. Now, let me make A of omega real simple to start with. Let's just start off with some DC gain of A0, and let's have a single pole, an RC time constant. So let's make this replace that. Okay? Now let's analyze that a little bit, okay? And let's skip the second for a little bit, okay? So we can work with the frequency response of this, what is it equal to? It's A of omega is equal to A0, the DC gain, times the transfer function of this RC network. And we know what that is. It's 1 over 1 plus j omega RC, which is equal to A0 times 1 over 1 plus j omega over omega P1, right? And there we could do this also in S domain, right? If we want to do A of S, the Laplace transform S from your days when you were doing your calculus, right? This is equal to A0 times 1 over 1 minus S over P1. So when S equals the pole, this thing goes to infinity, and that's the definition of a pole. So this means there's a pole at P1. And how do you get back and forth between these two? You know, the way you go back and forth is that A of omega is equal to A of S, Laplace transform S, where S equals to j omega. Okay. So we can go back and forth between these two things. Okay. What's important, as we said before, is the location of this pole. Right? If this pole is in the positive, the right half plane, the P1's on the right half plane, if we put this is supposed to be this is a block, like a transfer function, right? So if we have an impulse, a spike, go into a block that has a right half plane pole, a pole in the right half plane, we'll get an exponential increase from that excitation because P1 is positive. If P1, or now let's call it P2, if it's negative on the other hand, we'll get a decaying exponential when we impulse it. Okay? So something exponentially growing is unstable. Something exponentially decreasing, stable. So we need to have all our poles in the left half plane. So that's what we'll check for stability. We'll check, what we're going to do now is with feedback, we're going to watch what happens to the poles of our circuit. All right? For this circuit right here, what's P1 equal to? P1 is equal to, we can see, minus 1 over omega P1. Or no, minus P1 equals minus omega P1. And omega P1's positive. So for this circuit right here, our pole is equal to minus 1 over RC. So this circuit right here has a pole in the left half plane, so it's stable. You know that. If you impulse a circuit like this, or what happens? It decays, right? It doesn't grow. Okay, so RC decays. Okay. Now let's go in and let's go back to our same old. Let A of omega equal this, and let's calculate. Let's work with Laplace transform. We always can go over to frequency response if you want to. Let's calculate the Laplace transform ratio between V out of S, transfer function, and V in of S. It's equal to A of S. And that's simply A of S. I mean, this is just, remember our original thing was 1 over F times T over 1 plus T, right? This is what A of A equal to. The closed loop gain looked like this. Well, T is equal to AF, right? So I could make this equal to A over 1 plus AF, right? So that's what I'm using right here. So I just got rid of the F here. I just cancel out the F with the F inside that T. Okay. Let's now let A be A of S now. Let's A have frequency dependence. So we end up with A of S, or 1 plus A as F times F, and we can write it back like this again. If we do it like this, we're back to a function of t of s again, right? Where t of s is equal to a of s times f. Let a of s be equal to a0 over 1 minus s over p1 over 1 plus a0 over 1. This is the new a of s here, right? Which has this frequency dependence. Let me factor out the a0, and I get the frequency independent part. I get a0 over 1 plus a0f. So this is the old frequency independent term that we had before, right? This is the same as 1 over f times t0 over 1 plus t0. Let t0 be the frequency, let equal to t of omega at omega equal to 0. So this is the DC gain, closed loop DC gain. Now let's factor out all the frequency independent parts, and I end up with this. 1 over 1 minus s over p1 times 1 plus a0f. Okay. Now, if we look at this, so where is the pole now? It was at p1 before we had feedback, right? Now, with feedback, the pole has moved to p1 times 1 plus a0f, right? Or p1 times 1 plus t0. Okay? So in other words, what's happened to our pole? So we're beginning to see that the poles are moving on us, right? We started off with the pole at P1. That's without feedback. Okay, so this was just when we had the circuit like this. I put some feedback around it, feedback amount F. And what happened to the pole? The pole moved. Okay? It moved to the point P1 times 1 plus T0F. So it moved more and further to the left half plane. It became more stable. Went to a higher frequency, right? Remember what P1 was equal to. P1, so where is the 3 dB frequency with a pole out here? We started off with a 3 dB frequency at P1, right, which is equal to 1 over RC, okay, minus 1 over RC actually, all right, and what we moved it to, so this is to 1 over RC times 1 plus T0. So this pole, so if I look at the feedback with feedback, what happened? Where's the 3 dB frequency? It's moved out. So let me plot that separately. It's moved out to P1 times 1 plus T0. Or T0, well, let me, or 1 plus T0 times 1 over RC. No feedback. The 3 dB frequency is at 1 over RC. With feedback, it's moved out to the loop gain times 1 over RC. So it's moved way, way out by the loop gain. Wow, this seems great. Why did you use this when you use your projects, right? All you do is put feedback around it, and all of a sudden you get this much more loop gain, okay? Or this much more frequency response. What are we trading off? What have we lost? Gain. What's the gain here? A0. What's the gain here? A0 divided by 1 plus T0. The bandwidth went out by 1 plus T0. The gain went down by 1 plus T0. So we can plot these on the same curve, on the same place, the same curve. In other words, if we drop the gain down by the loop 1 plus T0 factor, the bandwidth goes out by 1 plus T0. So if you have a one-pole roll-off like you do here, you can see what happens. The bandwidth just kind of, the new bandwidth is set by where you intersect the one-pole roll-off. So we often see curves like this. The bandwidth increases out to this point where you sort of intersected the initial fall-off. Okay? So, great. Bandwidth went up, but gain went down. The usual trade-off. Negative feedback trades gain for everything, right? It traded gain for better input and output resistance. It's now trading gain for better bandwidth. Okay? So, important point. All right. Now, next. We call this the root locus. When you plot something like this as a function of the loop gain, what you're plotting is a sequence of steps of where the pole moves as you change the loop gain. Okay? So that's what's going on here. So I just did a second ago. And I guess this is the picture I just showed you. Okay? What happens if we have... Okay, now, this is all very fine. Okay, well, let me go back. Okay, let's look here. This is all fine as long as T0F is positive. That's true for negative feedback, right? T0F is positive for negative feedback. Because what I did, remember, I said this is a positive number. I said this is a positive number. Then I differenced here in my little differencing network, right? So it's overall negative feedback. What happens, however, if this, let's say, instead of having positive here, I had negative here? Let's just do that. So instead of 1 plus T0F, A0F, rather, sorry, A0F. Instead of having 1 plus A0F, I'll have 1 minus A0F if I change the polarity anywhere inside here. Okay, let's say I change the polarity of this gain right here. What happens then? P1, instead of going to the left, being more stable, starts going to the right. When is it right on the boundary? Right on the boundary when A0F equals 1. Right? So if I have positive feedback, I'm actually okay for a while. I can have positive feedback as long as the loop gain is less than 1. You see that? As soon as the loop gain becomes equal to 1, I become marginally stable. And as soon as the loop gain becomes greater than 1, then I'm over in the right half plane. So this is the stability condition. We're okay with positive feedback as long as the loop gain is less than 1. As soon as the loop gain gets greater than 1 and I have positive feedback, I'm toast. I've got a pole in the right half plane. Okay, so this all works for a single pole. In fact, for a single pole, so now let's look at we know that we never have a problem with changing polarity, right? If we plot phase, right? So let's say here's omega P1, and we have minus 90 degrees of phase shift. We start with 0 degrees of phase shift. This is theta now, phase shift. With one pole, we never get to 180 degrees of phase shift. We never get to be an inversion. We never change the polarity of this A. But what happens if we have 3 poles, for example? If we have 3 poles, I get 90 degrees from the first pole, I get 90 degrees from the second pole, and as soon as I get 90 degrees from the second pole, I have 180 degrees of phase shift. So now the theta is equal to minus 1 at this point right here. So that means my basic amplifier has changed polarity. It's gone from being at low frequency, it was nice and positive. But as soon as I get 180 degrees of phase shift, which will happen, as soon as I get exactly 10 times above the second pole, right here, I get 180 degrees of phase shift, and the polarity of my feedback network is now turned from negative to positive, right? You know, I'm talking about feedback now, right? So I have, here's my little A of omega. Here's the feedback. Here's my little differencing network. Minus, plus. I start off with everything, this being positive, this being positive, but as soon as I get 10 times above the second pole, this becomes, the phase shift of this becomes negative. So now I have a positive feedback loop. So now what happens, as soon as I have positive feedback, poles are starting to move over into the right half plane. This is always going to happen, right? You're always going to have probably a couple of poles. You're probably going to have a lot more than a couple of poles, as you well know in your projects, right? So you can see what the answer is. How do you make a circuit ever work?
Question.
Yes.
Um,
Where's it coming from?
well, the pole change from positive to negative ones when it gets to 180 degree, right? So what happens if you have like 5 poles and then it's go down to 360? So does it mean that from negative 1 it changes back to positive 1?
Yeah, you're okay again. Yeah, exactly right. So finally it goes back to positive 1 again, and after 7 poles or 6 poles, it's back to negative 1 again. So here's the problem. The problem is when you get the phase shift to be exactly -1, and it has to be exactly -1. It can't be -1 with a phase shift to it, because that still doesn't add up positive feedback. Any phase shift makes it. It's got to be exactly -1, which will happen at 180 and 540 and so on. The question you got to look for is, where is the gain large, right? Where is the most gain? Is it the most gain at the lowest frequency where you first turn? And certainly if you have a set of poles like this, it's where the largest gain you get is, because the gains falling off will be at the lowest frequency one. But let's say you had gain somehow or other that peaked up way far out. Well, it'd be out there where that phase shift was 180 degrees where you'd have a problem, right? But generally, we worry about the lowest one because that's where the gain is highest, and that's what gives us the most problem. Okay? When you design an oscillator, what you do is you design something like this, and you find the lowest place where you turn negative. That probably has the most gain, and that's where you'll oscillate at. Exactly that frequency. Okay? All right. Now, here's the really complicated thing. I got 3 poles. Let me just tell you this. I start off with 3 poles on the axis like this. What happens to these poles when I start putting feedback around it? What's the root locus of these poles as I put feedback around this basic amplifier? I'll tell you what they do. What these poles will do is this. This one goes in this direction. These two come together, okay? Then they split, and I think they do this. They go off like this, okay? Wow. Okay, so how did I figure that out? There's actually a set of rules. It's in your book. They're called root locus plots. And you can sort of do a geometric interpretation. Poles kind of, as you go up and put more gain, this is increasing T now, right? That's what we're doing. We're increasing the loop gain. Poles kind of push each other apart, okay, right? And at the infinite, this one goes, I think they end up with asymptotes at 120 degrees apart. So that's the asymptotes where this thing ends up going to, like that. If you have a 0, let's say I had a 0 sitting out here. What will happen then is this pole is kind of attracted to the 0, okay? And I guess these two poles would come together and they would split and do something, okay? And stuff like that. Keeping track of what happens with multiple poles and zeros is tricky, as you can see. There are a set of geometric rules, and like I say, you can look in the book. We're not going to do that in this class, but if you're interested, you can read that chapter and sort of see what happens to poles. I'll just give you some answers, what happens, okay? Typically, if you've got more poles than you have zeros, one of those poles is going to end up over in the right half plane. If you have more zeros than poles, in actual fact, you'll stay stable, because all those zeros will attract the poles and it kind of cancels them out, okay? That's real rigorous, but that's how it works. Okay, right?
Question?
Yes.
How do you create more zero than poles?
Not easily. You'd have to do our kind of circuits. That never happens, right? Okay, we'd have to use some active circuit with some. It'd be tricky, right? Typically, what will always happen is we'll end up with, because you end up with gain, right? You know, more zeros and poles. I mean, as you go to higher frequency, the gain's increasing. Right, so that's some very weird situation, right? For us, the gain always drops with a higher frequency. Right? Okay, this business of figuring out stability with multiple poles and zeros, as you might guess, is really complicated stuff. There's classes on this. I don't know what is it? It's control theory. What's it? 120 something or other, right? If you really want to get into this and worry about arbitrary poles and zeros and multiple feedbacks and all this kind of stuff, there's Lyapunov stability criteria that you can apply. I mean, there's some heavy machinery to figure out this answer, because this is control theory, okay? Fortunately for us, we do a really simple case, okay? The only case we worry about is real axis poles, right? And we don't care so much about the zeros, but the real axis. And that simplifies the analysis substantially, okay? So our stability criteria becomes quite easy, okay, because of this very simple case that we take, okay? So what do you have to look at? Clearly, the important thing to look at is if this is our loop gain, we're looking at, in fact, this kind of shows you part of what we need to worry about is what happens in that denominator. So this is the transfer function of the closed loop response, right? And you can see it's the denominator where the issue is, right? And so this can never equal to -1. If t of s ever equals to -1, that's when we're in trouble. So that can only happen, okay? Or in other words, to keep this thing stable, what we can do is we can make sure it stays stable if. So here's our condition for stability. If the loop only the wrong thing with this stability criteria is it's backwards, right? Oh, no, that's right. I'm stable. Yeah. Here's our condition. It's a kind of reverse condition. If the loop gain is greater than 1 at the frequency where the phase is minus 180 degrees, then the circuit's unstable. Okay? So in other words, all we have to do to check is we find the frequency at which the loop gain with the phase shifts 180 degrees, and then we check to see if the magnitude is greater than 1 or not. If it's greater than 1, we're unstable. So this is our stability criteria. This is our simple one. Okay? There's much more other ones you can do. There's a Nyquist criteria, which is a way to test stability, and you basically do a polar plot, and you watch what happens as it goes a function of frequency. You see how many times it goes around -1. If it's an odd number of times, it's okay. If it's even number of times, it's not okay. So stuff like that, and that works for arbitrary poles and zeros. We won't do that. Okay? We will just do this. Okay, right? All we need to look for is a look at the gain. So in other words, if I give you a plot of the loop gain, now remember it's the loop gain I'm talking about now, equals a of omega times f. And I show you the plot like this, okay? And I look at the phase shift. So these are the Bode plots. Remember our good old Bode plots. So the Bode plots, well, let me sort of draw a cruddy one. Let me. Okay, so here it is. Here's the Bode plots of a three-pole response of the T. So let's let f equal to 1. So if f equals to 1, the A of omega is the same, okay, as T. All right, so this is equal to T of omega then, for f equal to 1. Can we check to see if this is stable? What do? We look and see where the phase shift's 180 degrees. We go up here. We go over and look, and is that gain at that point greater than 1 or less than 1? If it's greater than 1 at this point, if 1's down here, this thing's unstable. If it's less than 1, it's stable. And I'll say one final thing now. If we ask for more gain, closed loop gain, right, A0, let's say we want it to have to be larger. That's equal to 1 over f, right? So if I want gain to be much greater than 1, I make f smaller, right? F should be, I want a gain of 100, a closed loop gain of 100. That means f needs to be 0.01. If f is 0.01, what happens to this curve? It drops down by f, right? So as you ask for more closed loop gain, you have a smaller feedback factor, and the circuit becomes more stable. What's the limiting case? If f goes all the way down to 0, then what happens? If f is 0, then we're always stable. Well, what's that mean? It means we have no feedback anymore, right? We got rid of the feedback. So that's one way to make your circuit stable.